So if you're revolving y equals f of x, or z equals f of x, around the x-axis, then you get x equals x, y equals f of x cosine theta, z equals f of x sine theta. If you're revolving instead around the y-axis, then it's best to express this as a function of y. Then you can do the same thing. Right. And we'll come back to these surfaces of revolution at the end. So this is one common method of parameterizing surfaces. All right. Now, way back early in the semester, we were talking about functions of two variables, z equals f of x, y. We talked about tangent planes. Okay. So what we had back then the equation of a tangent plane is z minus z naught. So the equation of a tangent plane at a particular point, z minus z naught, is df dx times x minus x naught plus df dy at that point y minus y naught. So we know how to define a tangent plane if the surface is described this way, but what if the surface is defined parametrically? So in that case, we need to use the parametric equations. So suppose you have some surface. Here's a point on the surface. And you get this point by plugging in certain u and v values into your parameterization. And here's what you can do. If you hold u constant, busted.
Can't do that.
What?
Can't do that.
Oh. Well, I'll try it again, see if he sets off a siren again. Maybe it'll go over Billy Club and beat my ass. So,
I wonder if I start recording the cop. I wonder if I start recording the cop, how he'll react.
All right, I guess it's okay. So if you hold u constant, you get a curve, and you're letting v vary. So here u is equal to u naught. Here we have v equal to v naught, and u is allowed to vary. Then we get two different curves. And each of these curves at this point has a tangent vector. So we'll call this one RV, because v is what's varying. And this one we'll call RU. Okay. And we can write down what these tangent vectors are. Okay. So RU is the partial derivative of x with respect to u, evaluate u naught v naught, then y with respect to u, and zu. So all the partial derivatives with respect to u. And then RV, partial derivatives with respect to v. All evaluated at u naught, v naught. Okay. Now, once we have two vectors in the plane, can anyone remember from Calc 3 how we get the equation of the plane? That's right, you did. All the more reason to know.
A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0.
Where you get A, B, and C from?
Your
Cross product.
normal.
Yes, the normal, which is the cross product of, yes. Okay, great. So, the equation of a tangent plane is normal vector dotted with this vector x minus x naught, y minus y naught, z minus z naught is equal to 0. And n is a cross product of RU and RV. Now, what you can do is, if your surface is described this way, then you can come up with a simple parameterization. X equals x, y equals y, z equals function of f of x, y. So x plays a role of your u, y plays a role of your v. And what you can do is you can go through the same process. You can compute your vector. So RU in this case is going to be 1, 0, fx. RV is going to be 0, 1, fy. And then the cross product, RU cross RV, is going to be, so we'll get minus fx, minus fy, and 1. So when you take so we'll call that n. So then when you compute this, n dot product of x minus x naught, y minus y naught, z minus z naught, you get exactly this. So it's all the same. We're just working with more general description of surfaces than we had before. So any questions about equation of tangent plane? So anytime you have a parametric surface, use your partial derivatives of your parametric equations with respect to u and v. That gives you vectors, RU and RV. Take the cross product, that gives you the normal. And then you can get the equation of a plane in the usual way. All right. So, for instance, suppose we have these parametric equations. X is u squared, y is equal to v squared, z is equal to u times v. And we'll let u, v vary over the square, 10 by 10 square in a uv plane. And let u naught, v naught be 1, 1. So that means that the point, x naught, y naught, z naught, where we're going to compute the tangent plane, is just 1, 1, 1. Yeah, how boring. So you compute your vectors, partial derivatives. So we take the partial derivatives of all of these with respect to u. So that would be 2u, 0, v. RV would be 0, 2v, u. And now we plug in the u and v values at our point. So that's going to be 2, 0, 1, and then 0, 2, 1. So now we can get the normal of the tangent plane. And we're going to get minus 2, minus 2, and 4. So now we can write down the equation of the tangent plane. So it's going